Hi, my name is Grant Veazey and I am Senior Design Engineer at AES Solar. I'm going to talk a bit about solar thermal and solar PV involved in the Heat for Cool project. So firstly, we have solar thermal, which is providing heat to drive the absorption heat pump system for cooling. So as an overview, with solar thermal, it exists to generate heat from solar energy. It's tried and tested, mature technology for renewables. AES Solar have been doing it for over 40 years, and evidence of it being used goes back to Roman times. A variety of panel types available on the market, most commonly flat plate collectors, evacuated tube collectors, PVT, which is a combination of electrical and heat energy, and concentrated collectors, which can generate extremely high temperatures. Some versions of solar thermal can actually generate temperatures in the thousands of degrees centigrade for mining applications, for example. But more commonly, we're looking at building applications for to 90 degrees centigrade. Design factors that are usually considered are the location, the climate there, the space available, mounting options, and the planning, building regulations locally. We also want to think about what temperatures we need and how much energy we need, as well as the local building regulations and building itself. Is it well insulated? Is there room for large heat storage? And what kind of pump pipe runs would we need? Long pipe runs mean less efficient system. Here we have an example of the top left, a flat plate collector, which is manufactured by AES. We have an evacuated tube collector, which instead of an insulated box, you have a vacuum within glass tubes. And on the right there is the standard form of solar thermal, with a solar thermal array circulated by a pump with valves to control it, with the heat transferred to some kind of store. And that heat will then be transferred on to be used or to another technology to use it. And here's the energy flow with the Heat for Cool solar thermal solution. Do we have the panels? This is the panels in Valencia. So the energy is generated from there. All of that is transferred to the store. And flow rates can be altered, for example, to reach the required temperature. If there's a shortfall, you can also get heat from the heat pumps, the air source heat pumps. And that heat is then mostly transferred to the absorption heat pump machine to provide space cooling. Can also be used directly for domestic hot water, especially in winter when cooling demand is less, or for space heating. So the theory, you have heat generated from solar, transferred to a storage medium, which is then used for absorption heat pump to generate cooling, or for hot water, or for space heating. Any shortfall provided from other sources. You also have the SIBEMS, the Self-Correcting Intelligent Building Energy Management System, which is able to use various methods to optimize the control for efficiency and also to ensure that the required comfort levels are achieved for the occupant. The benefits of this system is the provision of zero carbon energy for space cooling, in addition to space heating and domestic hot water. You have lower operating costs, reduced carbon emissions resulting from running the system, and also an increased solar heat load in summer that can be used for cooling, which can result in a higher fraction overall. So the diagrams here represent that. So the top diagram illustrates typical domestic hot water and space heating scenario where you have consistent domestic hot water demand over the year, with space heating increasing into midwinter. Difficulty to match that to solar is that you can have solar providing most of the heat needed in summer, but then as the solar availability drops off, the load increases. So over the year, your solar fraction can be quite low. But if you were to increase the amount of solar available, you would have too much in summer, and that solar would have to be dumped, or you would have to deal with the high temperatures some other way. So that reduces the efficiency of the system. It increases the cost per kilowatt hour. So the viability of the system reduces. So the lower diagram illustrates the benefit of adding cooling as a load. So then you can generate much more solar in summer and use that for cooling. And then as that cooling drops off, you then have a space heating demand, which also can use a lot of solar. So you can increase the amount of solar provided to the building and still use most of it throughout the year. So this increases the amount of energy demand that solar can cover, and also increases the solar fraction of that solar. So the cost per kilowatt comes down, and the amount of heat used from elsewhere throughout the year is reduced. And we've seen an example of this where the absorption heat specialist Fahrenheit are working with the project in Toledo to add the ability to use solar for cooling to an existing system in order to justify the increase of solar energy that's obtained from the solar system, solar thermal system. Here's a quick idea of the schematics. So you have a normal solar thermal, you have the array, you have the pumps and controls to circulate it, and you have, in the case of Valencia, an innovative storage system where you can vary the amount of storage capacity depending on how much solar is available. So if there's less solar, you can reduce the volume of storage to achieve higher temperatures. And when there is more solar available, you can increase it and make sure you're extracting the most from the array. And this is a specification at Valencia. We have 20 AES 2.5 AR flat plate collectors for a 36 kilowatt peak system, coupled to a maximum storage capacity of 3,500 litres, although that can be vary between as low as only 1,500 litres, where there's less solar available. And we have the intelligent building management software. So the solar PV system is designed to provide electricity to the air source heat pumps, which in turn heat phase change material heat batteries. PV as well, commonly known, well-proven technology that generates sunlight into electricity. Generate DC from the panels, which is then often converted to AC to be used in mainstream appliances and grid-connected loads, or it can be used directly as DC. Very reliable, there are various forms available, and the considerations are similar to thermal. Location, the climate in the area, how much sun is available, is it often cloudy or rainy, which may affect the output, the mounting options, any local regulations, and also how much energy is needed and when is it needed, and how well does that match up to the solar that we can generate. So the theory with heat for cool is converting the solar into DC electricity. That DC electricity will be delivered directly to a DC input of a heat pump where required, and that is used to generate heat, which charges a phase change material storage, which in turn can be used to generate heating and hot water. Any shortfall in heat can be provided from other sources, and you also have the self-correcting intelligent building energy management software system, which can maximize the efficiency whilst ensuring comfort of the occupants. So the benefits, again, reducing the cost and the carbon emissions associated with the space heating and domestic hot water, and also coupling with the benefits of the phase change material heat storage. With heat for cool, the main idea is to deliver as much DC electricity directly from the solar as we can, so you remove the need for an inverter, which potentially can reduce equipment costs and also remove some conversion efficiency losses. There are some issues with that. Heat pumps often require a high startup power, which is with much of the year, especially if the space is restricted, the solar will not achieve. If you have a big enough solar to achieve that more often, then you will also have a lot more spare solar, or times when the solar generation will be curtailed if there's nowhere else it can be used. For retrofit, space often restricts the maximum solar output. Also, a solar solution sized for a good solar fraction may often be insufficient to get that minimum required energy to start up the heat pump. There's some other facts that affect the design of the heat for cool solution. The DC inputs are often non-standard, they're not so common, which means although they're simpler than AC, they also are more expensive and less sophisticated. Solar inverters transferring from DC to AC are now very low cost, and very, very high efficiency, over 99% in most cases. They also come with enhanced performance, individual panel performance optimization, and monitoring, which is not commonly available with DC equipment. So this is the energy flow of the solutions in the HeatProCo pilot sites. We have the solar PV, which can send electricity direct to the heat pump. Can also send AC electricity to the building when the heat pump doesn't need it, to be used within the building or be exported in exchange for a tariff. Equally, the heat pump does have an AC input, so if there's a shortfall from solar, it can pull energy in from the grid. The heat pump then sends heat to the PCM storage, which in turn provides the heat for the loads in the building. This is now an image of the schematic at the Poland and Sofia pilot sites. So at Warsaw in Poland, we have a 14 kilowatt solar PV system with high efficiency modules on a flat roof mounted on A-frames to get the optimum angle. And they're connected to the heat pump and to the three-phase electricity grid supply in the building. In Sofia, we also have a similar 14 kilowatt PV system spread across multiple roofs, some sloped roof and also some flat roof in a different direction, connected to the heat pump and also the single phase grid connected building supply. The benefit here, especially of having the AC equipment, is that it does include that monitoring and performance enhancement that means you can get the most out of multiple roofs and the panels are facing different directions. If you used a simple DC charge controller scenario here, you would be in a situation where there'd be significant mismatch losses, string mismatches. It would really curtail the output of the solar PV system. So the combination of both systems here is really worthwhile. So that's my description of the solar thermal and solar PV systems we've provided as part of the HeatProCo project. Thank you.